This lecture is going to be on units 17 and 18, which is a resistive inductive series and parallel circuits. The R stands for resistive, the L stands for inductive. So here we have our standard series RL circuit. Now remember, when we have a purely resistive circuit, the voltage and the current waveforms are in phase with one another, or in other words, they're 0 degrees out of phase with one another. That means they both start at 0 at the same time, they both hit their maximum positive peak at the same time, they reach 0 again at the same time, their maximum negative peak at the same time, and 0 again. So they are in step with one another. And also when we have a purely inductive circuit, the current lags the voltage by 90 degrees. This means that the current does not reach its zero crossing until 90 degrees later after the voltage has reached its zero crossing. Now, if we have both a resistor and an inductor in a series circuit, what do you think happens as far as the phase shift between voltage and current? Well, it's going to be something in between 0 and 90 degrees. So here, our zero crossing for our current, blue is our current waveform, is somewhere in between 0 and 90 degrees. And where that is depends on how much resistance and inductance you have in the circuit. So looking at our standard series RL circuit, we'll notice that there are a bunch of new circuit values. Oh boy. We have Z here. This is something known as impedance. This VA is something known as active power, not active power, apparent power. PF stands for power factor, and angle theta stands for angle theta, which is the phase shift between voltage and current. And we will go into more in depth in those later. So the first circuit value that we're going to solve or talk about is impedance, Z. Make sure I'm spelling that right. Impedance. Impedance symbolized by the letter Z. I is already taken up by current, and it has units of ohms. And impedance is the measurement of total opposition to current flow in a circuit. So impedance is the measurement of total opposition to current flow in a circuit. Now remember, both a resistor and an inductor have some ohmic value associated with it. That ohmic value is how much it resists current flow. However, we cannot simply add these two together. So I cannot say that my total impedance Z is 70 ohms. So Z would not be 70 ohms for this circuit. Now why is that? That is because of that phase shift between the voltage and current for the inductor. Because of this phase shift that the inductor causes, we have to now treat resistance and inductive reactance as vectors. So if I was to draw each as a vector, here my resistance R is going to be at 0 degrees because voltage and current are 0 degrees out of phase in a purely resistive circuit. And now I'm going to draw my inductive reactance, X sub L, at positive 90 degrees. Why? That's because voltage and current are 90 degrees out of phase in a purely inductive circuit. Now notice I have what looks to be almost a right angle triangle. So I'm going to complete this triangle right here, like this. And this new side of the triangle is my impedance, Z. adding resistance and inductance, but we are adding them, inductive reactance, but we are adding them vectorially. And so the sum of these two vectors would give me this resultant vector. And that will be our impedance Z. So how do we find this? We find this using Pythagorean theorem. So you know from Pythagorean theorem that Z would be equal to the square root of R squared plus my inductive reactance squared. So that is how I would find inductive reactance. It is square root of R squared plus X of L squared. That is our general formula for finding impedance in a series RL circuit. Our next circuit value, right here, VA, this is known as apparent power. So apparent power, make sure I'm spelling this right, I'm horrible at spelling. Apparent power, symbolized by the letters VA, also has units of volt amps, symbolized also by the letters VA. And so this value is found by multiplying the total applied voltage and current in the circuit. So our apparent power VA is equal to the total voltage multiplied by the total current. Now do not confuse this with true power P and reactive power, inductive reactive power bars L. These are three separate things. Okay? They all represent a different thing in the circuit. However, they are all power values, so they are related, and once again they are related vectorially. So if I was to draw a vector of each one of these, I'm going to have my true power P at 0 degrees. I'm going to have my inductive reactive power bars L at positive 90 degrees. By now I should know why that is. That's due to the relationship between voltage and current. And then, once again, these are two vectors. We're going to add the two together. My total resultant vector is going to look like this. And this total resultant vector between true power P and reactive power bars L is my apparent power VA. So we essentially have another equation for VA, where it would be the square root of P squared plus bars squared. Once again, from Pythagorean theorem. However, I do recommend you simply just use this formula. In general, all types of power are simply volts times amps, voltage times current. So for the true power here, it's going to be the voltage drop across the resistor times the current through the resistor. The reactive power from the inductor is going to be the voltage across the inductor times the current through the inductor. The apparent power VA is going to be the total voltage multiplied by the total current. You can, however, also use this equation if you would like. next circuit value is power factor. So power factor, symbolized by the letters PF, and thank God it has no units associated with it. That's because it is a ratio. We're essentially dividing two of the same type of thing. The units then cancel each other out, so power factor has no units. And power factor is defined as the ratio of true power to apparent power. So our power factor PF is equal to our true power P divided by our apparent power VA. And so power factor, this is an incredibly important concept in circuits. What it basically tells us is how well the circuit is creating power that can be used or converted into some usable form. Remember, of these three power values, true power P is the only power that can actually be converted to some other useful form. So that means that is the amount of power. So we have electrical power that we put into the circuit. The true power P is the power that can be converted to some other form, something like putting electrical power into a light and getting light out, or putting electrical power into a motor and getting rotational power out. That rotational power we get out of a motor would be its true power P. And so, for this reason, power factor can be expressed as a decimal or percentage this percentage tells us how much of the total power in a circuit can be used or converted to some other usable form. So power factor tells us how much of the total power in a circuit can be used or converted into some other usable form. So one way to think about this, actually before I get to this analogy, first let me talk about a circuit. So let's just say some circuit, we have some total apparent power in the circuit being produced is 1,000 volt amps. And the true power P is 900 watts. So, whenever we're paying for power, we always have to pay for all of the power being supplied. So, as a customer, you're going to be paying for 1,000 volt amps of power. However, due to whatever type of circuits you have loaded up, you can only actually convert 900 watts of power in your circuit. So you're paying for 100 volt amps, but can actually only use 900 watts of power. So my power factor in this case for this circuit would be 900 divided by 1,000, which would give me 0.9 or 90%. So that means only 90% of the power in this circuit can actually be used or converted into some other useful form. However, you have to pay for 100% of it. So A good analogy for this is using beer. So you go to the bar and you pay for a cup of beer. So here's my cup of beer. Now I pay for a whole cup of beer. However, let's say we have a terrible bartender and you get a lot of foam. So here's my beer, here, and then the rest of this, the glass is filled with foam, like this. So 100% of this cup right here is filled with beer. However, only about 50% of it is a liquid, the other 50% is a gas of foam. So you're only going to actually get to drink 50% of this beer. So the beer that you can actually drink is like the true power of P, the power that you can actually use. The fizzy part that you can't drink and goes away is sort of like the reactive power. Now, the reactive power is needed to complete the drink. Obviously, you don't want your beer to be flat, you want it to be fizzy, so that fizz is part of the drink, but you can't actually, if it's too fizzy, that goes away and you can't actually drink it. And then so the total drink would be your apparent power VA. Once again, you're going to pay for the entire cup of beer, but you're only going to be able to actually drink about half of it. So I don't know, that was a sort of interesting analogy I saw used for the relationship between apparent power, true power, and reactive power. You pay for the entire thing, but there's only a certain amount you can actually use. And power factor basically tells us the percentage of the power in a circuit we can actually use or convert to some other form. So our power factor is the ratio of our true power to our apparent power, or P divided by VA. And our final new circuit value here is angle theta. Symbolized by the symbol for angle and the Greek letter theta. And this has units of degrees. Angle theta tells us the angular displacement by which the voltage and current are out of phase with each other. Now remember that a circuit with both resistive and conductive components, the phase difference between the voltage and current will be between 0 and 90 degrees. So an easy example would be if we take a purely resistive circuit. Here's the voltage E. Here's the current I. Angle theta of a purely resistive circuit would be 0 degrees. Now, if we have both a resistor and an inductor in a circuit, it's going to be somewhere in between these two. So the question is, how do you calculate that? It's based on our power triangle. So we had our power triangle here, where we had our true power P, our reactive power, our inductive reactive power bars L, and then our apparent power VA. Angle theta is simply the angle that apparent power makes with true power. So we got to do a little bit of trigonometry to find this equation here. So I'm looking at true power and apparent power. So I have, in relationship to this angle, I have the adjacent side and the hypotenuse. So I have the adjacent side and the hypotenuse. Out of our three trigonometric functions for SO, TOA, cosine is going to make ca. So cosine of angle theta is equal to adjacent over hypotenuse. I need to solve for angle theta. So solving algebraically for angle theta gives me the inverse cosine or the arc cosine of the adjacent divided by the hypotenuse. Now, in the case of this triangle, the adjacent side is P, and my hypotenuse is the apparent power VA. So our equation for angle theta is the inverse cosine of P divided by VA. But what is P over VA? P over VA is my power factor. So I can simplify this even further and simply say that angle theta is the inverse cosine of the power factor. Now remember, this is not cosine, this is inverse cosine. So on your calculator, you gotta put the second or the shift key and then hit cosine to get to this inverse cosine. These are two different things right here. So now we've described all of our new circuit values. Let's go ahead and let's solve a basic series RL circuit. First thing about a series circuit that we should all know is that current is the same everywhere. For this circuit, the total current has been given as 4.88 amps. So that means that we have 4.8 amps for the resistor, and we also have 4.8 amps for the inductor. Next is sort of up to us as how we want to find the rest of these circuit values. That's the hard part about solving circuits. It's kind of non-linear as far as how you want to solve for things. First, let's start with the resistor, since we all are pretty familiar with those. So first, the voltage drop across the resistor, ER, is going to be the current times the resistance. So that's 4.8 times 30, and that's going to give me a value of 144 volts. I'm going to say the power collapsed because once again we can still use the idea that the power across each component should equal our total power. In this case, the true power plus the reactive power should equal our apparent power. Next, let's look at the inductive values. So the inductance L is equal to the inductive reactance divided by 2 pi times my frequency. Once again, if the frequency of a circuit is not given, assume that it is 60 hertz. So this is equal to 40 ohms divided by 2 pi times 60. And that's going to give me an inductance of 0.106 henries. Next, the voltage drop across the inductor, E sub L, due to Ohm's law, would be IL times X sub L. Remember, in general, for Ohm's law, if you have units of volts is always equal to units of amps times units of ohms. This has units of amps. Inductive reactance, X sub L, has units of ohms. So if we multiply those two together, we should get volts. So that's going to be 4.8 times 40, which gives me a voltage of 192 volts. We'll worry about power later. Next, let's find the total impedance, Z, of the circuit. That is equal to the square root of the resistance squared plus the inductive reactance squared. That's equal to the square root of 30 squared plus 40 squared, which gives me a total impedance of 50 ohms. Next, the total voltage of the circuit, E sub T, would be equal to the total current times the total ohmic value of the circuit, which is our impedance, Z, 4.8 amps times 50 ohms, gives me a total voltage of 240 volts. Now let's take a look at something here. You should all remember Kirchhoff's voltage law. Kirchhoff's voltage law stated that the total voltage drops in a series loop should equal the total voltage. So the total voltage is 240 volts. Is that equal to the sum of each voltage drop? So ER plus EL? Well, ER is 144, EL is 192. What does that give us? That gives us a voltage of 336 volts. So something seems wrong right here, right? Is Kirchhoff's voltage law not a law? I mean, a law means that this is always true, no matter the condition or no matter the circumstance. So what's going on here? Now remember, we have to treat every circuit value as a vector. So that means I have ER, the voltage drop across the resistor, at 0 degrees, and I have to have E sub L at 90 degrees. So that means my total voltage, if we were to add these vectorially, is going to look like this. So our equation for our total voltage in an RL circuit is simply the voltage times the current of the resistor, so that's 144 volts times 4.8 amps, and that's going to give me a true power of 691.2 watts. Next, our inductive reactive power, VARS L, is equal to EL times IL. What you're noticing for any type of power value is always volts times your current. But depending on which volts and current you're multiplying gives you the different type of power. So this is 192 times 4.8, which gives me a total reactive power of 921.6 bars. Remember, bar stands for volt amps reactive. And then finally, our parent power of the circuit, which can be thought of like the total power in the circuit. That's going to be our total voltage times our total current. So 240 volts multiplied by 4.8 amps gives us a total apparent power of 1,152 volt amps. Now remember, power across each component should equal the total power being supplied by the circuit. And so that means our total apparent power should be equal to the vectorial sum of the individual powers from each component. So we know our total power is 1,152 volt amps. Is it equal to the vectorial sum of these two? If we did everything correctly, that should be true. Add the two together, and I do in fact get 1,152 when I vectorially add the power and the reactive power. I'm sorry, the true power and the reactive power. I'm even more specific with P. It's now the true power. Next, let's look for the power factor. The power factor tells us the percentage of power in the circuit that can actually be utilized or converted into some other form. Our power factor is simply the ratio of our true power P divided by our apparent power VA. So our true power P is 691.2 watts, and we're going to divide that by an apparent power of 1,152 volt amps. We divide those two, and I get a power factor of 0.6, which is also equal to 60%. The decimal or the percentage is fine. So that tells us that only 60% of the power being produced in the circuit can actually be utilized or converted in some other form. The other 40% is essentially trapped in this inductor where the magnetic field expands and collapses, expands and collapses, and we cannot actually extract that energy stored in the magnetic field. Now it's needed for the circuit to work, so we need to have this here, but once again, only 60% of that power that's being supplied by the circuit is power that can actually be converted to some other form. But we do need to have this reactive power here for this type of circuit to work, whatever circuit that might be. This is actually very representative of a motor. A motor has a very large inductance, but also has some resistance associated with it. So you'll find for motors, being that they do have large inductances, we can never extract 100% of the power we put into a motor. It's always going to be some partial percentage of the total power that we can actually extract from a motor. And then finally, we have angle theta. The phase voltage and current, it is simply the inverse cosine of our power factor. So that's going to be inverse cosine of 0.6. So whenever you're putting it in your putting a calculator, you cannot put the percentage. You need to put the decimal answer when you input this into a calculator. Do not put 60 because you should get actually an error if you try to put 60. Always got to be some number less than 1. So we put that into our calculator. And I get 53.13 degrees. So that means the phase difference between voltage and current is 53.13 degrees. So if I was to graph this, it would look something like this. So we always start our voltage at 0. Voltage is our reference. Here is 90 degrees. So if I was going to put my current, graph my current waveform, so half would be 45, so about right here would be 53.13 degrees. So that's how our voltage and current waveforms would look if we graph the alternating current waveforms. And so that completes our lecture on series RL circuits. Next we're going to look at parallel circuits. So bear with me here while I erase everything and get the parallel circuit up on the board. So here is a standard RL, resistive inductive parallel circuit. Thankfully, there are no new circuit values. The only thing that's changed is the configuration of the circuit. We're now in a parallel circuit. Remember, parallel is defined as having more than one path for current to flow. The only thing that's going to change as far as our equations, all these equations are going to stay the same. The only thing that's going to change for equations is for our impedance Z. I'm not going to do the derivation for this. It is 1 divided by r squared plus 1 divided by x sub l squared. So 1 divided by the square root of 1 divided by r squared plus 1 divided by xl squared. And this is absolutely, positively, utterly disgusting to use. I will not test you on this equation. There will be a couple of homework problems where I'll have you use this, but on the test I'm not going to expect you to use this. So please practice it, know how to do it. If I was to put this into a calculator, it would be 1 divide key, square root key, left parenthesis, 1 divided by r, close the parenthesis, square it, plus left parenthesis, 1 divided by xl, close the parenthesis, square it, and then I believe I need to close the parentheses and then hit the equal sign. So as you can see, this is absolutely disgusting to put to a calculator. There is a couple of homework problems where you'll need to do this, but I'm not going to expect you to do this on the test. There are other ways you can find this without using this equation. So once again, that's the only change. Everything else as far as the individual values, the equations stay the same. It is just now a parallel circuit. Remember, important rules for parallel circuits. Number one, most important rule is that the voltage stays the same. So if you have one voltage value, you now have the rest. So I have 240 volts here, and I have 240 volts here as well. So now it is up to us to find the rest of the circuit values. First, let's deal with the resistor. So the current through the resistor, IR, is going to be equal to the voltage across the resistor divided by the resistance R. 240 volts divided by 15 ohms gives me a total resistance of, total current of 16 amps. I'll say the true power P for last. So now let's deal with the inductor. Here the inductance was given as 0.0531 henries. So now let's find the inductive reactance, X sub L. That's equal to 2 pi times your frequency times your inductance L. Once again, if a frequency is not given, we always assume that it is 60 hertz because that is the frequency of our electricity here in America. So this is 2 pi times 60 times 0.0531 henries. And that gives me a total inductive reactance of 20 ohms. Next, the current through the inductor, I sub L, is going to be the voltage drop across the inductor, E sub L, divided by the inductive reactance, X sub L. That is going to be 240 volts divided by 20 ohms. Gives me a total current of 12, sorry, not total current, and the inductive current of 12 amps. Now, next, we probably all want to try to find the total impedance Z right here, but I really do not want to use this formula. I want to try to avoid this formula. So how else can we find the impedance Z? Well, let's go to our general rule, our general Ohm's law. So in general, for Ohm's law, units of volts is equal to units of amps times units of ohms. Now we know that impedance has units of ohms. So if I take units of volts and divide it by units of amps, that should give me ohms. So Z, our total ohms of our circuit, should be the total volts ET divided by the total current. So this is another far more simpler way to find the impedance. Problem is, for this circuit, we have the total voltage, but we do not yet have the total current. However, remember one of your major rules for a parallel circuit is Kirchhoff's current law. Kirchhoff's current law states that the sum of the individual currents through each branch should equal the total current flowing through the circuit. So the total current should equal the sum, but remember this is now a vectorial sum. So it's no longer simple addition, it's a vector addition. Once again, we have to treat all of these circuit values as vectors. So that means that my current IR to the resistor is at 0 degrees. The current to the inductor IL is at 90. And then of course, we add these two vectors together, and that's going to give me my total current. This is a right angle triangle. We use Pythagorean theorem to get that side of the hypotenuse, where the hypotenuse in this case is my total current. So IT is going to be equal to 16 squared plus 12 squared, which gives me a total current of 20 amps. So now we can find the impedance of the circuit, the total ohmic value of our circuit. Our total voltage is 240 volts, and our total current is 20 amps. It's going to give me a total impedance of 12 ohms. And so we also notice, remember, in a parallel circuit, the total ohmic value of the circuit should be less than the ohmic value of each individual component. The lowest ohmic value that we have is 15 ohms on the resistor. So we know that our total ohmic value of our circuit should be less than 15 ohms, which of course it is. That is a way of checking to doing that we did this correctly. So now let's deal with all the power values. Our true power P is equal to the voltage drop across the resistor times the current to the resistor. So 240 volts times 16 amps gives me a total true power of 3,840 watts. Next, the reactive power of the inductor, bar L, is E sub L times I sub L. So 240 volts times 12 amps gives me a reactive power of 2,880 bars. Next, our apparent power of our circuit, VA, is always the total voltage multiplied by the total current. Total volts, 240, times the total current of 20 amps. Gives me a total apparent power of 4,800 volt amps. Next, our power factor, which is the ratio of our true power to our apparent power. Remember, once again, power factor tells us the percentage of the power in the circuit that can actually be utilized or converted to some other form. For true power is 3,840 watts. Our apparent power is 4,800 volt amps, which gives us a power factor of 0.8 or 80%. So that means 80% of the power in the circuit can actually be utilized, which is pretty good. This type of circuit would be very indicative of a shunt connected DC motor. Or not a DC motor, an AC motor. And then finally, angle theta, the phase difference between our voltage and current. It is the inverse cosine of our power factor. Technically, I shouldn't be calling this inverse cosine, it's called the arc cosine. Inverse cosine is actually something different. It just usually when you see the -1, that means inverse, but this is really called the arc cosine, so any mathematicians, I apologize. So this is the arc cosine of 0.8 for power factor. Once again, make sure you're not putting just cosine in your calculator. You're using the arc cosine, or the cosine with that -1 power. Typically, all calculators require you to push the second or the shift key to get to that. And so that gives me an angle of 36.87 degrees. And so, if I was going to graph the relationship between voltage and current and draw their AC waveforms, look at something like this. Once again, voltage is always started at 0, that's our reference, and then the current in blue is going to look something like this. So here is 90 degrees, about halfway would be 45, so 36 is about right here. So it's going to look something like that. Actually, that's going to be further. So it's kind of hard to draw this accurately just on the board. So something like that. So about the current 0 crossing is going to start about right here at about 37 degrees. So that concludes our lecture on RL parallel circuits. Hopefully this is getting less and less awkward. I miss you guys. I wish you guys were here. It's far more fun when you guys are here, but yeah, let's keep going. We're done for the day, but let's keep going through this semester. Adios.